If you could shrink yourself down, smaller than a grain of sand, smaller than a strand of hair, and step inside the device you're using right now, you would find yourself in a city filled with towering structures, highways, and billions of intersections. Yet, this city has no moving parts, no gears, no motors. This electronic city is completely silent, but it also functions very identically to your brain. And the fundamental building block of this technology is called the transistor. Art direction plus. It is the reason why computers went from looking like this to this. This is probably faster than the biggest supercomputer in the 1960s, 70s. So, how did it happen? Let's go back to the early 1940s, when computers filled entire rooms, even buildings sometimes. They weighed tons and were made out of vacuum tubes. These were light bulbs. They were kind of like switches. They turn electricity on and off. Simple, right? But they got incredibly hot. Now imagine needing 18,000 of these vacuum tubes to do basic math. Like just imagine a calculator, a size of a huge room, just to do basic math. Not happening, right? Now, scientists hit a wall. Computers couldn't get faster or smaller because of the hardware was physically too big and naturally unreliable. Then came 1947. A few scientists at Bell Labs wanted something that would work like a switch but didn't take up that much space. So they experimented with something called semiconductors. These are specific type of man-made materials that can change their conductive property on demand. Just like that. Which simply means that scientists could control the flow of current through a silicon rock just by touching it with a tiny electrical charge. And that's how it worked like a switch. And hence, the silicon transistor was born. So how does it work? How does a solid block of rock act like a switch without any moving parts? Now, silicon is a semiconductor, which means it needs very little energy to let current flow. But we can mix it with other materials to exactly control how much energy will be required. This interesting method is called doping. Not that doping, I know what you're thinking. Now, using this, we create two types of transistors. One is a simple N-type or negatively charged, which means it's like an on switch that closes when energy is applied. The other one is P-type or positively charged, which means it's an off switch that only switches on when you apply energy to it. When we apply a positive electrical voltage to the gate, suddenly the path is open. Electrons move from one side to another. If you cut the power to the gate, the field collapses. The bridge disappears, the electrons stop moving. The switch is off. Unlike most switches, which need a human finger to flip it, physically, a transistor is a switch that is actuated or activated just by electricity. It's a switch controlled by another switch, providing electricity. And this is where we enter the realm of logic. We use switches to represent binary. If a current is flowing through it, it's a 1, and if no current is flowing through it, it's a 0. Simple, right? By wiring transistors together in specific patterns, we create something called logic gates. It's a lot like programming. Now, let's visualize something as simple as an AND gate. Imagine a single wire with two transistors, one after another. For electricity to get through from the starting point to the finishing point, the first transistor must be open and the second transistor must also be open. If you only open one, the current is blocked by the other. Simple, right? So this gate effectively makes a decision. I will only output a 1 if input A and input B are both 1. 1 plus 1 equal to 1. We are talking about logic, by the way. Now imagine an OR gate. Here the transistors are side by side on two different paths. Electricity can take the route on the left or the route on the right. If you turn on the first transistor, the current goes through. If you turn on the second, the current still gets through. Now this gate will output 1 if input A or input B is on, or even both are on. So fair game. Finally, there is something called the NOT gate. It is simply an inverter. It uses a transistor to ground the signal. So if you give it a 1, it spits out a 0, and if you give it a 0, it spits out a 1. Just like your kid. Now these simple rules or gates and or and not are the founding blocks of every piece of software ever written. Actually, इतना ही simple था. फालतू में fail हो रहे हैं. So now let's do something interesting. Now let's make a small calculator to add 1 plus 1. To get that answer, the inputs A or B or 1 and 1 pass through two simple logic blocks at the same time. The sum XOR gate says 0 and the carry gets 1 0, which is binary for 2. So now this circuit is called the half adder and has around 10 transistors. मतलब 1 plus 1 करने के लिए 10 transistor लगते हैं आपको. So but if you combine around 2000 transistors, you get an old school calculator that can do basic addition and subtraction. Cool, right? And then if you combine 14 million transistors, you get the first NVIDIA GPU, which could play and run 3D games at around 480p in the year 1999. But if you chain 90 billion transistors, you can render ray trace lighting in real time, simulate weather patterns, and train programs more intelligent than a human being. The explanation I gave you with electrons building bridges, gates collapsing and closing happens at a speed that's impossible for us to imagine. Actually, बहुत मुश्किल. In the 1950s, you could hold a single transistor in your hand. Today, this thing actually has billions of transistors. Now imagine that. More billions. When you read that the processor speed is 5 gigahertz, that is the speed of the clock. It means that 5 billion times every second, the computer checks the state of these switches or transistors. 5 billion times a second. Wow. Now, every time you type a letter, every time you click a link, every time you tap, literally billions of tiny switches wake up, do the math, verify the logic, and go back to sleep. Cool, right? And they do this in all the time it takes you to half blink, not even fully blink. उससे पहले हो जाता है. It's quite literally the peak of human achievement, actually, if you think about it. सोच लो यार, इसमें क्या क्या हो जाता है आजकल. Now, we hope you liked this video because it took a lot of time and effort, and do comment if you need an entire series explaining the inner working of electronics. Check out our channel for more amazing videos, and until next time.